Hello guys, so this is continuation from my second research vlog on NeRFs, and this video will be a deep dive on the research paper and continuation of that vlog. If you didn't see the vlog, check it out here and have a great time.
Okay, so this is the original paper from 2020 that introduced NeRF for the first time. And as we can see, in abstract, NeRF is an algorithm to represent a scene using fully connected deep neural network whose input is a single continuous 5D coordinate, so this XYZ plus viewing direction coordinate input. And output of this network is this volume density and view-dependent emitted radiance at different location, which we can think about basically the accumulated color that we should take from this particular location into the pixel representation of the particular view of the scene. So let's look into details. So let's first discuss the input. So input is 5D because we have 3 XYZ coordinates, so that's our basically the starting position for which we are sourcing the value of the array. And then we have this radial and azimuth coordinate that describes from which point of view we're looking at the scene. And that's our input basically too. And we are expected to receive as an output this volume density and RGB color that we can then render into the particular picture and to represent a view. So how does that work step by step? First we take camera rays, we march them to the scene, we will see exactly what the equation looks like for that, and we sample the 3D points that we're gonna input into the network. We then use these points and we get the corresponding to the viewing, with the corresponding to the viewing directions as input to the neural network to produce an output set of colors and densities. So here we use our neural network representation to get the particular density and color that we should accumulate for a point in 3D space. And then we use volume rendering to accumulate these colors, generate 2D image from these colors and densities, and we compare this 2D image to the collected 2D images that are our training set. So here we see training set of input images. We see that they have different positions of the scene, around the scene from which we are viewing the scene. And then we can pick some random position, let's say here for example, right? And we render the image just by casting the rays from this particular point into the 3D space and then sampling the points that the rays went through. Then accumulating the values through the ray into the pixel of the camera point of view and generating the view from that. So that's how the in general this works. And most important contribution, in my opinion, that NeRFs presented was applying this positional encoding to map this 5D coordinate input into a higher dimensional space. This is very similar to what transformers do to encode the positional encoding of the token at the beginning. We will see that they actually use very similar equation to do this encoding. So this was originally present in Attention is All You Need paper, and they also use it here to encode this 5D feature. And with that they were able to get this high quality result that we saw on the website. So this is very important. We will see the difference between using or not using this positional encoding. One could think that this doesn't really matter that much because we have these fully connected layers. They can take this 5-dimensional input into 256 dimensions, the next layer, right? So they expand into the multidimensional space. But when that is happening from the 5D into this bigger space, actually in the course of training there is this collapse that happen, and with the collapse that happens we use much worse we learn much more worse representations. So if we enforce this automatically to be in higher dimension to generate the high dimensional output of the image, then this helps a lot in generation. We see how. So this is the discussion of related work. We'll not go through this, but what we focus on is how exactly this neural radiance fields works. So as I said, we have this input vector xyz, and we have this 2D viewing direction. And this viewing direction obviously is represented as a vector d, and vector d is a unit vector in 3D. So basically what they do, this is a radial coordinate system. Assume r is equal 1, and they basically calculate this direction using these two values and r equals 1, and then they normalize it such that the length is 1, no matter what's the direction, right? So then we get this d that basically is telling us which way the ray is casted into the picture, right? So we will see how we use that d later in the rendering pipeline. And basically our network then represents the transformation from this x comma d to c comma sigma, and where c is the color output and sigma is the density at a particular point. And we can think about this, basically this volumetric density, as how much we should really take into account this color. So how much is luminance is generated by this sigma, and is this point that should contribute a lot to the value of the pixel in the generated image output or not? So basically, this sigma helps us to eliminate and not consider the points in 3D space where basically there is nothing. There is a translucent space, right? There is no object there. This helps us to not consider these points, and instead we consider points that are actually like reflecting the light into the ray of the camera. So then they discuss the architecture of the network, and it's very simple architecture. It's 8 fully connected layers with ReLU activations and 256 channels per layer. This is not a convolutional neural network, so that's an important thing. And these 8 fully connected layers output sigma and 256 dimensional feature vector, okay. And then this feature vector is concatenated with the camera ray's viewing direction. So note that the sigma is calculated only with xyz. It does not use the ray direction, so these last two information elements, to calculate the sigma. Sigma is just xyz. And then we take this 256 already processed feature vector, and then we concatenate these additional directions, and we calculate the with one additional fully connected layer and 128 channels in that layer to output the view-dependent RGB color. So you see that sigma is one transformation before the RGB color is returned. So that's how the architecture of the network works. I think it's very reasonable architecture, nothing crazy here. So then they discuss how to do this volumetric rendering, and this obviously was not something that we do every day. I don't think if you're not in 3D graphics, you probably have no idea what that is, and I didn't have idea what volumetric rendering is, but this equation explains it pretty well with all of this text. So let me try to synthesize this for you. So basically what we do, we have this origin point, so this is where our camera is casting the rays from, and we have this d vector that we already discussed, this unit vector with the direction of the camera rays, and we are just returning this r of t, which is basically the position at which we are sampling the point, and we see that with time we are just moving with this unit vector down from this, in whatever direction the camera is pointing, we are moving in this direction from the origin point, and we sample these different points at different times t. Obviously t is small, right? So we are just changing this by some small amount to find this ray that we are for which we're gonna calculate the value for, and we have this basically t of t, which is telling us how much we should consider the particular value that we gathered at some point. And it's obviously calculated from the starting point to the ending point of the traversal of the ray. We are calculating the sigma value at that point, and we're calculating the color that is dependent on both the position xyz that is calculated by this r and also the direction. So this is basically this azimuth and radius coordinate. So with that we just sum this up, and we have an output color for a particular ray of camera. So this is a pixel that we're gonna generate and output in the 2D image. So we do that for all the pixels and all the camera rays that we're gonna generate from the when we do this volumetric rendering, and this way we're gonna retrieve an image from a particular position. Then the question is, right, because we talked a lot about sampling the points and pushing them through the neural network, we cannot do that like on all of the points because there are infinite amount of points, right? So we need to sample some points that are gonna represent the image well. So at first we use this semi-random sampling when we basically we have n evenly spaced bins around the array, and then we draw one sample at random from each bin using a uniform distribution. So this is explained by this equation here. So this way we have this continuous representation because it's a semi-random process. So this is very useful because we don't have discrete points at which we sample. It's not like we divided the space in some number of cubes and we take 1 point for every cube in the center of the cube. It's not like that. We just sample it randomly based on the ray direction, and that's how we do it at the beginning. We will see that they also have some specific sampling strategy that is later discussed that helps us improve on this result. So then what's important is that we can see that this positional encoding, as I explained, is what really improves the model. So this is the ground truth data, and this is their solution if they don't do positional encoding. We see that it's very blurry, and actually the positional encoding was the key to unlocking this high quality performance. On the other hand, this is how the model performs if we don't add the azimuth and the radial information for the point of view. So if we don't have that, we see that the lightning is not represented. Lightning situation in the scene is not represented well. Why is that? And intuitively, right, if we have set of images from one point of view and the opposite point of view, right, they will have different colors on particular objects in the scene because there are different lighting conditions from these different point of views, right? So if we cannot really if we cannot predict what should be the lighting because we don't have this information from which point of view we are looking at XYZ coordinate, right? Then we will just gonna take the average from all of the input space, right? But now if we have all of the pictures and we have this representation, we can use this view dependence representation to actually understand, okay, lighting is visible on this part of the view space, but it's not visible on this part. So if we are rendering here, we should render with lighting, and if we are rendering here, we should render with different lighting that does not include lighting that would be visible in these pictures, right? So this is very well seen how on this ground truth light is going from this way. So this particular element is shining a lot of light into the camera, and this is not represented here, but it's very well represented here in the complete model where they use both of these improvements, right? So this is why this additional information is important. So here they discuss also like the encoding of input coordinates helps us representing high frequency functions. This is very well seen here, and hierarchical sampling allows them to sample high quality, high frequency representation. And we will discuss both of those right now. So as I said, this positional encoding, what they do is basically they take this coordinate, let's say X or Y, for example, and they plug it in here into this vector of size L, and basically they just calculate cosinus and sinus, multiply this value by pi to 2 to the power of position in this vector, and this way they get this higher dimension frequency based encoding. And this is very typical. This is how the encoding of scalars happens a lot right now in neural networks. And it's originally from, it was used in attention is all you need, for example, but in other papers also, and this helps a lot to train this high frequency uniformly distributed bins, right? And that's great, but they improved on that with this additional strategy. So what they do, instead of training one NeRF, they actually train two NeRFs, so two set of weights in parallel, and they sample points using one of the NeRFs. They call it coarse NeRF. So they sample with the previous strategy, no change with no change with this strategy. And then they use the points they sample, so now they know sigmas, right? Because they sample points, they process the points, and they get sigmas back. So now they can take the sigma points and calculate the weights such that wherever there is high sigma, so there is important point that we should really consider, right? Then we have the high weight, okay? And if there is small sigma, then we don't really care about the point because it doesn't contribute to the final value. So we have small w, so small weight, right? So then they produce a piecewise constant PDF along the ray such that there is higher chance to sample a point from the place where the sigma is high. So then they use the second network that they train in parallel and sample points from that network using this new PDF. So with this new PDF, basically, they sample points specifically from along the ray where the sigma is high. So we can have one network that is focused on the representation that is like very general representation, and then they have this second network that focuses specifically on points. Okay, these are the points of interest, so we spam a lot of points in this point of interest and we have better details. And then they basically concatenate these two representations to get the final result. So when they render, they use basically all the points, NC plus NF. So these are the points from the small network, the first network, and these are the points from the second network with the PDF that calculated from the first network, right? And specifically there are, I think, 64 points sampled this way and 128 points or additional coordinates in the fine volume sphere, right? Okay, this is mentioned here, right? So there are 64 points sampled. So two times more points are sampled from using this PDF after already 64 kinda gave us the first overview of the space along the ray. And then after we do the rendering using these points and outputs from the network, we can just calculate the mean squared error between the image that is in the training set from this particular point of view and what actually the network rendered for this particular point of view from which the image was taken, right? So we just calculate the mean square error like that, and we do that independently. We first calculate mean squared error between the actual image from that point and what network predicted with this rendering pipeline from this coarse network, so the first network, and then from the other, right? So at the training time, we kind of separate these two and train them independently, and then after they are dependent based because this network is actually the results are based on this PDF from this network. But in general, we don't add these points together to calculate the representation, and they take mean square error, but we actually take mean square error independent for each network, and that gives us the final error for the image, and we minimize this loss to optimize the neural network architecture such that we can actually sample these points or whatever point of view. And the issue is, because we encoded the space in this neural network architecture, we have to train, as I said, every new neural network, and in fact in this method, 2 neural networks per one scene that we want to render. And the issue is these operations are not that cost effective. In practice, what they found is that this method at that time costed them to generate one single scene 1 to 2 days of training on NVIDIA V100 GPU, which is very, very high quality, best in class cloud GPU for neural network training. Okay, so we see that this model had very big problem with the fact that this was very slow to optimize. So that's it for the NeRF introduction. So here I will just take a brief pause to let you know that you can like this video, subscribe to my channel, and follow for more. And in the next step, we're gonna discuss this paper, which basically solves the problem of very long convergence. Okay, so this research paper from NVIDIA. So this research from NVIDIA allows us to generate these NeRF results very quickly. And as you can see, this is a real-time NeRF generation. So really in a few seconds, we have very high quality results. And this is incredible improvement over the previous results and previous techniques in NeRF. And we will see that this is very much related to how this positional encoding was done previously and how better we can encode the NeRFs with the technique that they presented here, which is called multi-resolution hash encoding. So let me just show you the paper here. So, okay, we see the paper, okay. So this paper basically introduces this hash encoding into the picture, and we can already see on this first table how big the difference is. So this is the picture that is trained for 1 second, for 15 seconds, and this is the results on this finer small detail. This is a gigapixel image, so this is very high resolution, and we see after 1 second we've got that, and after 15 seconds we already have these results. After 60 seconds this is the result and this is the reference. I don't see much difference, right? So this is a very big, very high quality reproduction, and this is basically on the task of super resolution, right? So we see that this is very good when it comes to this high quality encoding, and this actually is similar when it comes to NeRF, the standard Lego picture that we use. We see that after 1 second we already get that, after 50 seconds we have this, after 60 seconds we've got these results, and this is the reference, right? So we see that the reference is nearly perfectly matched after 60 seconds. They improved that because they basically had two main advantages. So they figure out this new idea of hashing the encodings and how they can do this effectively to encode sparse and coarse details and fine details. And also they obviously coded it on CUDA operations, so it's very fast because they are from NVIDIA, so they knew how to do it. As I mentioned, the results are really interesting. You can see that the hash table that they have has amazing results compared to, obviously no encoding doesn't work, but frequency encoding works somewhat, but with their encoding, with trained embeddings, the results are much better. And also the time, even without any embeddings, we just do the frequency encoding that we did previously, right? This is 12 minutes 45 seconds. For them to train that is 1 minute 47 seconds, and this version is 1 minute 48 seconds. Very high quality, better than this one, but uses nearly the same amount of parameters, right? We see that the amount of parameters is similar. Here we use much more parameters for embeddings, but we get better details, right? But at the same time, the speed is unparalleled. Yeah, like this is great. The speed that they got was because they applied this hash table lookup for embeddings, and specifically they also did something very surprising. They use this spatial hashing for 3D reconstruction, but they do not handle collisions in hashing. We know that hashing, basically the problem with hashing is that we have to handle collisions. Well, they don't handle collisions. They don't do probing, bucketing, chaining. Instead, they rely on neural network to learn to disambiguate hash collisions itself, avoiding control flow divergence, blah blah, reducing implementation complexity and improving performance. So they basically use the neural network and the gradient descent process to set up embedding in this way, such that even if there is collision, it doesn't impact the performance of the network, because the collision is between, for example, the important feature for point and not really important point. Let's say point that doesn't have high sigma, so it's not very important. So therefore, network only focuses to create embedding for the point that is important. So this way they manage to speed up the process very much. So how does it work in practice? So we take this image and we divide this image into this grids, right? And these grids, there are 16 of them. There are only 2 shown here, but there are 16 of these grids. And for these grids, we have this square. So let's say we have this x, right? And we want to have embedding for the x. This is our xyz point. We want to embed it, right? So then we find ourselves inside of different squares. For every square we have 4 points, and these points directly hash into hash table. This hash table has dimension of length 2, this f is 2-dimensional, and there are 16 of them, and for every point we can have this 2-dimensional vector. And then we do linear calculation, to interpolation, to calculate what would be the 2-dimensional embedding for this point, considering that this is a 2-dimensional embedding for this point, this is a 2-dimensional embedding for that point, right? So we just take this 2-dimensional embedding, calculate the linear value of this vector, and we basically concatenate together the representation that comes from this big grid, that comes from this big grid, and then we have smaller and smaller grids. So we have 16 level of varying size of this kind of grids, and all of them contribute to the final embedding that we input into our neural network, okay? We additionally can concatenate additional information E here as an input if we need to, but this is basically only task-specific additional information. So we focus only on this spatial 3D coordinate XYZ, and we see that this can be done with this interpolation strategy. So they use some special hashing function that you can analyze if you want to, and they say that they basically solve the collision. The collision is not a big deal, not important, because they have this implicit hash collision resolution situation. So let's read it through. So it may appear counterintuitive that this encoding is able to reconstruct scenes faithfully in the presence of hash collisions, because let's say 1 point hashes to the same square, right? So they have the same representation, right? But key to its success is that the different resolution levels have different strengths that complement each other. Okay, different resolutions, so we have this different size of these squares in this grid. Okay, so we remember about that. So what they say is the coarser levels, and thus the encoding as a whole, are injective. That is, they suffer from no collision at all. So basically this big one, there is no collision, right? Because we just encode this point into this one-to-one, right? So there is no collision, but the point is they can only represent a low resolution version of the scene, since they offer features which are linearly interpolated from widely spaced grid points, okay? So we have these features, right? We have 1, 2, 3, 4 features, basically, and we only interpolate this feature of this point from these 4 points, right? So these 4 points, basically, 4 times 2 is like 8 values, represent all of this by linear interpolation, right? All of this space, but when we go down then to the small grids, right? Let's look on the small grids. So conversely, fine levels can capture small features due to their fine grid resolution, but suffer from many collisions. That is, disparate points which hash to the same table entry. So what they mean, when we take the grid where there is like 16 by 16 pixels, right? We have our personal grid. There is only 16 other pixels inside this grid, right? But thanks to that, these values here, right? They can focus on this particular space in the 3D space. So this way they resolve this collision, and this allows them this significant speed up that they do. They also explain this linear interpolation that they do, and basically all of these operations are continuous, and we can apply chain rule to calculate gradients on all of this, so we can optimize these embeddings directly from gradient descent. So this improvement basically showed great results that actually made NeRF viable in all of different applications, because now training something for 1 minute and 1.5 minutes is reasonable, right? To get a particular scene. So I recommend reading this paper carefully. It's a long paper and there is a lot of technical details that you should went over, but I think I shared with you the general idea that they used in this paper. So that's it. Thank you so much for listening. This is my first deep dive on 2 particular research papers. Let me know if you like this way of looking into this research. If you have any comments, questions, ideas, share them with me down below, and please like this video and subscribe if you are interested in learning more. So stay tuned for the next episode coming next week. See you later.